Welcome to the course Material Science and Metallurgy. Myself, Dr. K. Vijaya Bhaskar Reddy, working as an assistant professor in the Department of Mechanical Engineering. Today, we are going to discuss the course called Material Science and Metallurgy. Okay, so first we will start with the introduction part of the Material Science and Metallurgy. Later on, we will go into main topics. Okay, in that, mainly the objective of course, mainly the course objectives. First, the course objective is first course objective: understand crystal structures, imperfections, and strengthening mechanisms. These are the things we will be covering in the unit 1 or module 1. In the course objective 2, learn phase diagrams, transformations, and iron carbide equilibrium diagram. And third course objective, study heat treatment and surface hardening processes. Next, know the classification and properties of ferrous, non-ferrous, and ceramic materials. And mainly, finally, the course objective, fifth course objective is gain knowledge of testing and characterization of the material. After studying this course, the student will going to understand, and they would be telling course outcomes from that. Explain structures, defects in the materials, and strengthening in metals and alloys. Strengthening mechanisms in metals and alloys. And they can interpret the phase diagrams and triple T diagram. The phase diagrams are iron carbon diagram. Okay, mainly the triple T diagram is nothing but time, temperature, transformation diagrams. And third outcome, apply heat treatment to improve material properties. Heat treatment is done to the materials to improve their mechanical properties. They will be able to identify properties of ferrous, non-ferrous alloys and ceramics, and conduct material tests and analyze mechanical behavior. These are the 5 course outcomes. Mainly, these are the module 1. We have crystal structures and imperfections and strengthening mechanisms, and we have Hume rotary rules as well, and equilibrium diagrams in the module 2, where we will be discussing different phase diagrams, lever rule, and different reactions called eutectic reaction, peritectic reaction, eutectoid and peritectoid reactions. Along with these, we will be discussing phase rule. And after discussing all these things, we will be discussing about iron carbide equilibrium diagram and triple T diagram, time, temperature, transformation diagram. This is next module 3 it discusses about the heat treatment processes, and in the module 4 we will be discussing cast irons and steels and ferrous and non-ferrous materials. In the module 5 we will be discussing material testing and characterization. Where material will be subjected to under tensile, compression load, okay, under shear load and impact load. These will be all these tests will be conducted. That is tensile hardness, Rockwell test, and micro hardness. Impact test called Charpy impact test and Izard impact test. The creep test called creep test, and based on that we will be drawing the creep curve, mechanism of creep, fatigue and fatigue test, and SN curve. Material characterization, that we will be using optical microscope to study the microstructures of a material, and in higher magnification we use scanning electron microscopy, not only for the microstructure, and we will be able to see through the scanning electron microscopy, we can see the elements present in a material. What are the elements and what is the weight percentage of the materials we can discuss. The textbooks you need to refer is an Introduction to Physical Metallurgy by Sidney H. Aviner textbook you need to follow. And you can follow the William D. Callister Jr., that material science and engineering. Material science and engineering. It is an introduction to material science. Okay. Along with this, you can, if you want to follow, you can follow the material science and metallurgy by Kodgiri, VD Kodgiri. Okay, where Everest Publishing House is publishing this textbook. And if you are there are a few reference textbooks, that is Physical Metallurgy by Raghavan, V. Raghavan, Material Science and Metallurgy by O.P. Khanna, and Lawrence H. Van Vlock, Elements of Material Science and Engineering. These are the textbooks you can refer for our courses. And these are the reference URLs has been given. If you want, you can go through these URLs so that you can have NPTEL courses. Coming to material science and metallurgy, it's a professional core subject for the first year, second semester people. For BTech first year mechanical second semester, we are offering this course, material science and metallurgy. What is meant by material science? We need to know what is meant by material science, and then we will be knowing what is meant by metallurgy. The material science deals with, it is a study of relationship between the structure, processing, properties, and its performance. See here, based on its crystal structure, okay, and we will be deciding how this process has to be carried out. Okay, so based on the process which we applied on a material to process, such that based on the process we will be having a different properties. What are the properties we will be achieving? And based on its properties, it relies on its performance. Okay, see here, it is an interdisciplinary field studying the relationship between the structure, processing, properties, and its performance of materials. Basically, the materials are metals, ceramics, polymers, and composites. And these will be based on this structure, processing, properties, and performance. We can design a new material, okay, or otherwise you can improve the material which is already existing. Okay, and you see here, the material science also defines the how atomic level structure dictates macro scale properties. What is meant by macro scale properties? Mainly the strength of the material and its electrical and thermal conductivity. These are the few examples. Okay, how the metallurgy. What is meant by metallurgy? Metallurgy is a specialized field within this, focusing especially on a special science and technology of extracting, refining, and alloying of metals, alloying of materials. Okay, this is how it depends. The material science, it is basically what is the structure of a material, what are the process we are going to adopt, and based on the process we will be achieving some certain properties. Based on its properties, the material will have its performance. Structure is nothing but crystal structure. The structure is nothing but crystal structure. What is crystal structure? We have basically simple cubic. Okay, simple cubic crystal structure. Second crystal structure we have body centered cubic structure. Body centered cubic structure. And the third one we have face centered cubic. Face centered cubic. Okay, and the fourth one we have the hexagonal close packed structure. Close packed structure. Along with this, we have different other varieties of crystal structures. However, in our engineering materials, most of the materials will consist of BCC, that is body centered cubic, face centered cubic, and hexagonal close packed structures. Okay, and processing involves the material is processed to have different mechanical properties or different mechanical different microstructures, and depends on the processing. What are the processings we have? For example, casting is on one of the process. Okay, welding is on another process. Casting and welding. Okay, machining we have machining process. Okay, and then we have forming operation, and we have forging operation, It means these are all mechanical processing. These are all mechanical processings we have. Based on its process, these materials will achieve certain properties. The properties are strength. One is on strength, toughness, okay, and its ductility, okay, and malleability. These are the different mechanical properties we have, and along with this, the material will have optical properties, chemical properties. Okay, these are all will get once the material is processed, will have certain properties. Okay, based on these properties, the material behavior, that is its performance, depends. Okay, why study the properties of materials? Why study the properties of materials? Since there are thousands of materials available, it is almost impossible to select a material for a specific task. It means we have abundant amount of materials we have, such that it is difficult for us to choose a particular material for a particular task, unless otherwise its properties are known. We have to know the property. Based on its properties, we can decide the material, which material it is suitable for our application. Okay, there are several criteria on which the final decision is based on. We have so many criteria will be there. It means, for example, a material is working under a normal atmospheric condition. Okay, there we will be choosing different kind of material. Whereas if a material is undergoing different kinds of loads, for example, flexural loads, it means that a material is experiencing both tensile and compressive loads. For example, a connecting rod will be experiencing tensile and as well as the compression loads simultaneously. So in that case, though it is working under the normal atmospheric conditions, there we have to choose different kinds of material property. Whereas a material which is just, for example, a material has to bear certain load, in that case we will be, for example, if it is on load and is on material, it has to hold its main aim of this material is to just hold certain load, that is W, weight. Okay, here there is no other loads which is acting on it, so it is an constant load which is acting. So here we need a material which can sustain these loads, whereas in case of tensile and compressive simultaneous loads are applied on a connecting rod, there the properties of material should be very strong, okay, compared to this material. Okay, and some materials we will be using at a elevated temperatures. Okay, elevated temperatures. Okay, a material which is working at higher elevated temperatures, there should not be any kind of losing of its properties, either mechanical properties, that is strength, toughness and hardness, these things, along with these thermal properties. Okay, it should not lose. In that case, the choosing of material is on different. Okay, there are less chances of material processing optimal or ideal combination of properties. It means that we don't have a material with optimal processing and ideal combination of properties. So we have to compromise such a way that, and we have to choose optimal material and with optimal properties by whatever are available with us. Okay, a need to trade off between the number of factors. A need to trade off between number of factors. A need to trade off between number of factors. There are, for example, you see here, though it is an beverage stored in this can, it is made of a steel. Okay, or otherwise it can be stored using aluminum. Okay, it means it is on metal. It is on metal. Whereas here, same beverage we are storing in a ceramic. It is on ceramic glass we are using. Okay, and same beverage we are storing in a plastic bottle. Okay, it means the processing of metal is different, and processing of ceramic glass is different, and processing of plastic is different as well. Along with this, the cost of the process also changes. Cost of the process also changes with respect to the material. It depends on its material price. Okay, along with this processing. Okay, you see here the metal are of aluminum, copper and iron, these kind of things, where we'll have ductile in nature, good thermal and electrical conductors. Okay, ceramics are oxides, nitrites, carbides. Examples are oxides, nitrates and carbides. Al2O3 is an oxide, Si3N4 is an nitride, and silicon carbide is an carbide. A glass that is of a brittle in nature, thermal and electrical insulator, high temperature application. We can use it in a high temperature application as well. Whereas the polymers, that is plastics, that is polyethylene, polyvinyl chloride, etc., high degree of plasticity. It will have high plasticity, and but which is having a low density. Okay, and along with these metals, along with the metals, ceramics and polymers, we have composite materials. We have a composite material. A composite is composed of two or more individual material which comes from a metals, ceramics and polymers. Okay, we will be mixing either metal or ceramic, either metal and polymer, Okay, or otherwise ceramic and metal. These type of combinations we will be using. Okay, metal matrix composite, polymer matrix composites, and ceramic matrix composites. These are the three types of composites we will be have. Will be using this material. The design goal is to mainly the metals are highly ductile in nature and as well as high strength in nature. Okay, but ceramics are high strength but low ductility. It means high brittleness these ceramics are having. However, the polymers are high ductile, okay, high ductile materials, but it can sustain up to certain temperature only, maybe around not more than 300 degrees centigrade. These polymers, okay, these metals can sustain more than 500 degrees centigrade also. However, the ceramics can sustain at around more than 1000 degrees centigrade. Okay, the design goal is to achieve a combination of properties that is not displayed by any single material. It means we are combining two materials such that we will be having different properties, and also it incorporates the best characteristics of each of the component of material. Okay, we will be using in case of composites as an particle. Okay, particles are reinforcing material. Reinforcing material. What about other one? Other one is a matrix material. Other one is a matrix material. Okay, these reinforcing were a particle. It means very short in size. Okay, and short fibers are viscous. The sense where will have L by D ratio is very high. Okay, and continuous fibers. Continuous fibers are very large in size. However, the length of the composite we have same length of the fibers we will be considering. And we will have laminates, sheet laminates we use. Sheet laminates we use. Okay, and that it means that till now we discussed different materials such that metals, ceramics, and polymers. Along with this, the combination of these metals, ceramics, and polymers is called composite materials. And advanced materials called the semiconductors we will be using in a semiconductors, that is electrical properties are intermediate between the metals and ceramics. Okay, biomaterials, it means biocompatible, bioabsorbable. Smart materials called sense change in environment. Shape memory alloys, piezoelectric ceramics, that is an quartz cloud. Okay, you see here a titanium material is used in case of hip joint. Okay, to replace that hip joint we are using titanium alloy. Titanium alloy is one of the best alloy. Okay, it is an biocompatible alloy. Biocompatible. And stainless steel 174 pH. This is another material we use in a biomedical applications. Okay, it means advanced materials we are also having. Okay, you see here the example of an shape memory alloy is that when you pull the material, it means it is a stretching of an spring, and if you leave it comes back to its original position. It comes back to its original position. This is an shape memory alloy. Another example you see here, it is also a shape memory alloy. A pin has been taken and its shape has been changed. However, after leaving for certain time, it is coming back to its original shape. That is nothing but shape memory alloys. In general, for example, we use candle. Yes or no? These candles are made of. See here, when we use this candle, candle is an material. When we lit this candle will get solid. It will get melts. Okay, now when you leave again, it comes back to original shape, that is a solid shape again. This is nothing but shape memory alive. Okay, the modern material, particularly we have to materials for storage and disposal of radioactive waste, particularly nuclear energy. Weight reduction in transportation vehicles. Weight reduction in transportation vehicles, that is automobile and aircraft application. And for solar energy and hydrogen fuel cells. Okay, these are the modern materials we need to develop for these applications. There are few materials we are using, however, we need to, there is this is a main thrust area we have, okay, to develop the modern materials. Mainly, as we have discussed, the main purpose of this discussion is to understand the material properties. Mainly, the material consists of an physical properties. The physical properties are called density, conductivity, acoustic properties, optical properties, and its specific heat. These are physical properties. When it comes to the mechanical properties, ductility, malleability, toughness, strength, stiffness, creep, fatigue, wear, these are all mechanical properties. However, this wear comes under tribological properties. Tribological properties. The electrical properties called electrical conductivity, resistivity, impedance, like this, etc. Chemical properties are called corrosion resistant properties, chemical stability, flammability, radioactiveness. These are all the chemical properties we'll have. However, among these, physical, mechanical properties are main important in our course. The next topic called structure of materials. We'll have, the structure is nothing but it's a crystal structure. As I already discussed, a crystalline material is one in which atoms are situated in a repeating or periodic array over large atomic distance. Okay, the distance is on large atomic, in the sense infinite distance, in which each atom is bonded to its nearest neighbor atoms. Half, this is half. This is a crystalline material. You see here, for example, if you observe this crystalline material, almost they have certain pattern of material. Okay, now there is no missing of atoms. Okay, when it comes to amorphous material, we have a vacancy or a space between the atoms. You can observe here, these are all the spaces available. It means they are not arranged in a particular order. It means the crystalline material is there now. This is particularly, it is arranged in a particular order, particular manner, whereas amorphous material is not like that. Okay, it is different. Crystalline materials are the metals. Almost all the metals like aluminum, copper, iron, zinc, okay, gold. Okay, these are all materials consist of crystalline in nature. What about the amorphous in nature? Amorphous nature, the ceramics consist. The ceramic materials will consist of amorphous in nature. Okay, you see here a crystalline material. If you observe structure of a material, if you observe, you see here I have drawn a particular cuboid where this material has x-axis, y-axis, as well as z-axis. If you observe, there is one atom. Even in this, there is one atom, second atom, third atom, fourth atom, fifth, sixth, seventh, and eighth. It means there are eight atoms at the eight corners of the cube. Okay, and this kind of material, this kind of atoms are repeated in infinite distance, not only in x-axis, y-axis, and z-axis. Okay, this is how the crystal structure will consist of. Okay, among these, if you take out this only these 8 atoms, for example, if you arrange 1, 2, these are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 atoms, okay, at 8 corners of the cube. Okay, this we call lattice points, and whole this one is called as a unit cell. We call it an unit cell. Like this we have, if for example you observe here, there are 8 atoms are there, and just next to this one again there are atoms in consequence. Sequentially we have the atoms. Okay, it means it's a repetition of these atoms is nothing but crystal structure. And only if you consider only one, then we call it an unit cell. Unit cell, the atomic order in crystalline solids indicates that small group of atoms, this is small group of atoms, form a repetitive pattern. It forms a repetitive pattern. A lattice means a three-dimensional array of points coinciding with atomic position. Is nothing but lattice. These are the lattice points. All 8. Okay. Under which we have, based on the arrangement of this unit cell, we have crystal structures are classified, that is simple cubic. It means cubic structures particularly. Simple cubic, body centered, and face centered cubic. Under simple cubic crystal structure, we have 8 atoms. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms are there. You see here 8 atoms at the 8 corners of the cube. 8 atoms at the 8 corners of the cube. You see here, first one is a simple cubic. This we call, as we have, okay, 8 atoms at the 8 corners of the cube, we call it a simple cubic structure. We call it is an 8, there is an 8 atoms at the 8 corners of the cube, as we have one, as we have atom 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 atoms at the 8 corners of the cube. Okay. The simple cubic crystal structure at standard temperature and pressure is that of polonium. Only material which exists at a particular standard temperature and pressure, the polonium exists in this simple cubic structure. And another one, cesium chloride, also exists and similar crystal structure under specific condition. It means the example for this simple cubic structure is that one is on polonium and second one is on cesium chloride. These are the two materials exist this simple cubic structure. Next one is a body-centered cubic crystal structure. It means there are 8 atoms. This is, for example, 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms are there. 8 corners of the cube. And there is a central atom between. If you observe here in this, it is represented 1, 2, 3, 4. 4 we cannot see that one actually. It is in the back side. 5, 6, 7, 8. 8 atoms are there. Okay, and in the middle we have another atom, that is single atom. Okay, you see here 1, 2, 3, 4, 5, 6, 7, 8. There is a middle one atom is there. It is difficult for us to calculate the volume of this one. So what we have done, we have made the arrangement in such a way that we have made in this manner. It means 1, 2, 3, 4, 5, 6, 7, 8 atoms, and there is another atom at the middle. So what we have taken, 1/8 of the portion of the material has been considered in each atom at the 8 corners of the cube. How many? 8 corners. And there is one atom at the middle we have. So 8 will get cancelled out. So we'll have 1 plus 1, that is number of atoms occupied in a cube is nothing but 2 atoms are there. 2 atoms occupied in a body centered cubic structure. Similarly, face centered cubic crystal structure. Face centered cubic crystal structure. You see here, there is 8 atoms. 1, 2, 3, 4, 5, 6, 7, 8. It means 8 atoms are there at 8 corners of the cube, and there are 6 atoms at the 6 faces of the cube. 6 atoms at the 6 faces of the cube. You see here 2, 4, 6. These are the 6 atoms at the 6 faces of the cube. Okay. So when we consider, if you see here, we have half of the portion at the face center. Half of the portion at the face center. It means how many are there? 1/6 into there is 6 atoms are there at the faces. 6 atoms. Each atom is occupying 1/2 portion. That means half of the portion. Along with this, we have 8 corners at the 8 atoms at the 8 corners of the cube, and each atom is occupying 1/8 of its portion. So that if you calculate, 8 will get cancelled out, and we'll have 1 atom plus 2 into 3, that is 3. So 1 plus 3 is nothing but 4 atoms are occupied in a face centered cubic crystal structure. Okay. Next comes the hexagonal close packed crystal structure, where you see here, this is in the shape of hexagon shape. These 6 atoms, if you join, which is having a hexagon shape. Even you can observe here, it is written hexagon shape. Okay. It means 6 atoms. 1, 2, 3, 4, 5, 6 atoms. Each atom is occupying 1/6 portion. How many atoms? 6 atoms. Plus, along with this, there is a central atom which is at the face. So half of the portion is occupying in this position. Okay. How many atoms? 1 atom at the top and another atom at the bottom. You can see there is one plane. Second plane is here. 1, 2, 3, 4, 5, 6. Likewise, we have, for example, if you consider 1 here, whole multiplied by 2. Why? Because this is one plane, second plane here. Okay, now plus we have 3 atoms at the middle here. If you can observe even this one. These are the 3 atoms. So plus 3. So here 6 are, it will go off. So we will get 1. Here 1/2 into 1, like we will get half only. Multiplied by 2. It means 1/2, 3 plus 3. 3 plus 3, that is number of atoms. 6 atoms we will get. Okay. 6 atoms occupies the hexagonal crystal structure. So these are the simple cubic crystal structure we have discussed. Body centered cubic structure and face centered cubic structure, and there is an hexagonal close packed crystal structure we have discussed. Okay. Now we will close this session here. Thank you. We will discuss the other topics later. Thank you.